We mentioned refraction in chapter 17. This is where light bends at the boundary of two materials. This can be seen if you look at something through water, or if you've ever placed a pencil in water or something like that. You can see that it almost looks like it breaks. We can quantify this bending using Snell's law. This states that N1 sine theta 1 is equal to N2 sine theta 2. This is saying that light will bend by an angle that's related to the index of refraction of the material. We're going to solve one of these problems using the tactics below. A laser beam is aimed at a 1 centimeter thick sheet of glass at an angle 30 degrees above the glass. What is the laser beam's direction of travel in the glass? Let's start by drawing out the layers. First, we'll draw the initial light ray at 30 degrees above the glass. Now, draw a line normal to the boundary. This next part can be tricky. You need to determine which way the ray is bending. The higher index of refraction has the smaller angle. Remember, each of these angles is measured from the normal. Label all angles of incidence and refraction, and use Snell's law to find the angle in the glass. So step 5, our equation is N1 sine theta 1 equals N2 sine theta 2. If N1 equals 1.0 and N2 equals 1.5, we have that. We also know that our theta 1 is going to be 60. Remember, these angles that we're using are measured from the normal, not from the surface. So since this is at a 30 degree angle above the glass, that means that it's at a 60 degree angle to the normal. We want to find theta 2. So we can say 1.0 sine 60 equals 1.5 sine theta 2. And we get theta 2 to be 35 degrees. What is the direction in the air on the other side of the glass? We'll start by drawing what we had before and following the rules to get the ray below the glass. We can then go through using Snell's law. So N2 equals sine theta 2 equals N1 sine theta 3. Third angle is in air, which is the same as it was before. So N1 and theta 3. 1.5 sine of 35 equals 1.0 sine of theta 3. We get theta 3 to equal 60 degrees. Exactly what it came in at. So we can say that theta 1 equals theta 3 because they are both in the same medium. Imagine you are underwater and you shot a laser pointer from your location to the surface. You begin shooting it straight up and then at increasing angles. We would see the light leaving the water and bending when it hits the air. However, the angle of the light in the air increases faster than the angle underwater. At a certain point, the light in the air will be refracted by 90 degrees. Whatever angle in the water causes this 90-degree refraction is called the critical angle. This is defined as the angle of incidence that causes an angle of refraction of 90 degrees. We find this angle using Snell's law. So we go from N1 sine theta c is the critical angle, equals N2 sine of 90, because that is the refracted angle that we're looking for. Sine of 90 is 1, which means that we can say that sine of theta c is equal to N2 over N1. There is also only a critical angle when you are moving from a higher index to a lower index. Any incident angle greater than this value will transmit light back into the medium. This is a process called total internal reflection. When you look at something in the water, if you were to try and grab it, your fingers would go right through it, almost like it's a hologram. This happens because the light coming from the water bends when it hits the air. Our eyes trace it back in a straight line, providing a false location. This is what we're seeing in this picture here. We have our object at point P, and it's sending light out in the water. The light hits the air and bends. Our eyes trace it back in a straight line. I know what you're all thinking, but are we able to mathematically quantify that? Of course we are. Before, we defined S as the distance to an object and S prime as the distance to the image. We can do that again here. So we have, this is from the object to the boundary, so that's S, and S prime is from the image to the boundary. Doing some math that you can follow if you care, we're able to find the image location as S prime equals N2 over N1 times S. Now, to some tangentially related examples. Away! You have a semicircular disk with an index of refraction of n equals 1.5. Find the incident angle for which the beam of light will hit the indicated point on the screen. We're given this picture. To do this, we're going to start with Snell's law. We have N1 and N2, but neither angle. However, one thing that's special about a semicircular disk has to do with the refraction angle. If we have a semicircular disk, light will enter it and it will bend. Light enters and it bends. However, the angle that it exits will be 0 degrees to the normal, which means that the light will follow a straight line as it exits the semicircle. What that's saying is this light here, it will come in and it will bend, but then as soon as it leaves the disk, it will keep a straight path. So we do not have to worry about an angle here. We don't need to worry about a second refraction. In addition to that, we also have two sides of a right triangle. We can use this to find theta 2. We have this triangle. This is our theta 2. This is 20 centimeters. and this is 5 centimeters. We're looking for this angle, SOHCAHTOA. We have those two. We want to use tangent. Tan of that angle is going to equal 5 centimeters over 20. Take the inverse of that, and we get that that angle is 14 degrees. So this angle right here, theta 2, that is 14 degrees. Now that we have theta 2, we can use that to solve for theta 1. We have Snell's law, N1 sine theta 1 equals N2 sine theta 2. We have N1, N2, and theta 2, giving us 1.0 sine theta 1 equals 1.5 sine of 14 degrees. Sine of theta 1 is 0.36, giving us an angle 21.3 degrees. A light ray enters a 45-90-45 prism and undergoes 2 total internal reflections. The result is a reversal in the ray's direction of propagation. Find the minimum value of the prism's index of refraction for these internal reflections to be total. Let's start by drawing this out. It says that the light undergoes 2 total internal reflections, emerging flipped. That would imply that this is the path that it took. If this is the path that it takes, then we know that the critical angle must be at least 45 degrees. We get that because we're able to get that because we can see that it's 45 degrees from the normal. We know that it is totally internally reflecting, and that angle is 45 degrees. So at least we know that at 45 degrees, we get total internal reflection. Since we know that theta c, our critical angle, equals 45 degrees, and we also know that N2 equals 1, because it's in air, we can use the equation sine theta c is equal to N2 over N1. Rearrange that and get N1 is equal to N2 over sine of theta c equals 1.0 over sine of 45. The sine of 45, as I'm sure you all know by heart, is the square root of 2 over 2. So we have 1.0 over the square root of 2 over 2. Flip that, and we get 2 over the square root of 2 times square root of 2, just to try and get the radical out of the bottom. It's good practice. Equals 2 root 2 over 2. We get that N1 must equal root 2. And square root of 2 is about 1.41. That's going to do it for part 2. We will pick this back up in part 3.